In this video, we'll talk about section 5.2 in our book, definite integrals. So we're going to first talk here about Riemann sums, what are known as Riemann sums. So if we start with any function, and this yellow curve is supposed to represent any function from x equals a to x equals b, which you can see with the green markings there, then it's called a partition when we divide that interval from a to b into n subintervals. And so those may or may not be the same width. So a partition just is a subdivision of that interval. So we take that interval and then subdivide it into n other intervals. So then we get that the area between the curve and the x-axis is approximately, so I'm trying to write squiggly lines there, and then we can write it in summation notation as the sum of, we'll say, k going from 1 to n of, and then it can be f of, I'm going to write c sub k. So what we choose to be the height of the rectangle doesn't matter. I mean, it can be just about anything. Left side of the rectangle, right side, midpoint, or random interior point. And then I'm going to write delta x sub k because I'm not sure whether those widths of the rectangles are all the same or not. So anything in that form where you've got a height times a width of a rectangle is what we call a Riemann sum in its most general sense. And we have here that x sub k minus 1 is less than c sub k is less than x sub k, just x sub k. So that is the point that we're using. So if I imagine, here's one subdivision there, then whatever you plug in for the height could be any point in that interior there. You could make a rectangle out of that. So it could be the left side, right side, midpoint, or just a random point in between there. Okay? So then we say further, if this limit, now first I got to define what this means. So we look at these variable widths here, and so we say it's called the norm. I'm going to write this double bar, so it's like a magnitude, and then this little Greek delta symbol. That is known as the norm. And that's equal to the largest of those delta x's. So I'm going to say the largest delta x sub k is known as the norm. So then we can say that if the limit, this is the most general sense that we can of these Riemann sums. If the limit as the norm goes to 0, so as the largest of those delta x's goes to 0, of our Riemann sum, f of c sub k times delta x sub k, k going from 1 to n, exists. So if that limit exists, then it is equal to the area. The area between the curve and the x-axis, which we will write as an integral from a to b of f of x dx. Now, area gets a little asterisk there because, as we have seen before, this is kind of a net area. So it's going to count when the curve dips below the x-axis there. It's going to count those rectangles as having negative area because remember, it's taking the f of x right there, which is a negative number, times the delta x to get that height. So to get that area. So this is known as the definite integral. That's our definition of the definite integral. It is that limit as the norm goes to 0 of this sum of infinite rectangles. So if that limit exists, so any curve, I'm trying to move my screen up here. So if this exists, and we can do this limit, we say if f is integrable, when the integral exists. So certainly any continuous function is integrable. So this is a known fact that is something you can use. Any continuous function is integrable. But that's not the whole story. There are sometimes even a discontinuous function can be integrable, but those are a little bit more exceptional. So for example, using what we know, if we were going to take, say, the integral from, we'll say, 0 to 4 of the absolute value of x minus 1 over x minus 1 dx. And to do this, we're going to use an area argument. So if you remember what this graph of absolute value of x minus 1 over x minus 1 looks like, it's our absolute value of x over x translated 1 to the right. So everywhere to the right of 1, this thing is going to be equal to 1. Everywhere to the left of 1, it's going to be equal to negative 1. So we can compute this integral using an area argument. That is, here's 0, 1, 2, 3, 4. Let me see if I can extend that curve a little bit. So it goes there. So if we look at the area between the curve and the x-axis between 0 and 4, granted we're going to lose the area underneath that one point where this is undefined, but remember, a point from your geometry days is infinitely small, so it has no area underneath a single point. So using an area argument, we know that the area of that rectangle here, because it's underneath the curve, is going to be a negative 1, and this rectangle that is 3 by 1 is going to be 3, and so we would say this integral is going to be negative 1 plus 3 is 2. So even though the curve is not continuous, this function is still integrable. Now, another point that we could do, so we could do one, something like the integral, say, of x squared minus 1 over x minus 1 dx, and let's do that from, say, 0 to 3. So you might see that there is a problem at x equals 1 because it's going to be undefined. If I'm trying to find a place to put my left hand here. So if we factor that numerator, we can see that that will cancel. So what this graph of this function that we have that we're trying to take the integral of is going to look like y equals x plus 1 from 0 to 3, 1, 2, 3. So at 3 it's going to be 4, 1, 2, 3, 4. So it's going to look like this line between these 2 points, except that at x equals 1, there's going to be a hole in the graph. So same argument that we had before with the first one we did, the area underneath that one point is nothing. So we can maybe divide this into a rectangle and a triangle, and using an area argument, we can say that rectangle there is 1, 2, 3 by 1, so that much is going to be 3, and the other one is, I think, a triangle is 3 by 3, so that's going to be 3 times 3 divided by 2 is 9 halves, or 4.5, and so using an area argument, we could say this integral from 0 to 3 is going to be 7.5. So even though the function is discontinuous at x equals 1, we can still integrate that function. That function is not continuous but is integrable. So continuity is kind of the gold standard. It's a higher standard than even integrability. And I'm going to go to a new screen here. Now, questions that we will explore later in this class that we haven't done before is, can we integrate over, say, a vertical asymptote. So can we integrate, say, from -1 to 1, something like 1 over x dx? Can we integrate something like 1 over x squared from, say, -1 to 1? And these are all fascinating questions that we will save for later, because we're not ready to talk about that yet. Just trying to keep you tuned in here. Let's go back to our idea of Riemann sums here. And so we're going to say if those delta x's, so remember we're talking about a Riemann sum is anything that can be written as f of c sub I times delta x sub I. So what we're doing is we're taking a height of a rectangle times a width of a rectangle and adding those up as a way of approximating an area between a curve and the x-axis, which we're going to call the definite integral. So if the delta x sub i's, because we have said that they don't all have to be the same, but if the delta x sub i's are all equal, then remember we called that a partition, that dividing the interval from a to b into subintervals, into n subintervals. But if the delta x sub i's are all equal, then the partition is said to be a regular partition. The partition is a regular partition. And we're not going to make a big deal out of that except to look at what our Riemann sum becomes. So remember we said that our limit as the norm goes to 0 of this crazy f of c sub I delta x sub I going from 1 to n. So when the norm goes to 0, that's assuming that these are all, whether these don't have to be the same width, but when it becomes a regular partition, then this becomes, instead of having to say all of that norm stuff, we can just say, take the limit as n goes to infinity of this I going from 1 to n of f of c sub I, and because it's a regular partition, all of the delta x's are the same, so we don't have to use that delta x sub I notation. It just becomes simpler and cleaner, and I think a little bit easier maybe to wrap your head around, at least when you're starting out. And that's maybe a nicer definition for what our definite integral is. So we have some symbolism, some language, some notation. Let's make sure that we understand what all of these things are and what we call them. So that funny stretched out S is an integral sign. And let's see, let me change colors there. So the B is the upper limit, and the A is the lower limit of integration. And the f of x part, what do I need red? So the f of x part here is known as the integrand. And this dx part is called our variable of integration, which isn't a big deal for us, but becomes a bigger deal when you get to Calc 3 and you start integrating with more than one variable. Let's see, what else can I say? So what we name this doesn't matter. So, whoops, let me move this up a little bit. So whether we call it the integral from a to b of f of x dx, or whether we call this the integral from a to b of f of t dt, or whether we call it the integral from a to b of f of y dy. So the name that we call that doesn't make any difference. So that those variables that we're integrating with respect to are sometimes just called the dummy variable. So don't be confused by what name we give that. That's just, doesn't matter what it is, it still means the same thing. So if we have something like, let me slide down here a little bit more. So if we say on this interval from, we'll say -1 to 4, then this limit, just the notation here we're talking about, the limit as n goes to infinity of the sum I going from 1 to n of 2, let's say, a sub I cubed minus 5a sub I plus 4, that whole thing times a delta x. So that is supposed to, you're supposed to be able to see that this is our f of x, and there is our delta x, making this a Riemann sum. And so as n goes to infinity, this will become the definite integral. And it will be from, we don't know where this goes from, so I'll just say a to b. But we can see here what the function is. It's going to be 2x to the third minus 5x plus 4. And then that delta x becomes a dx. Okay? Let's do a new panel here. And let's talk about some area under a curve. So we can use what we know about area under a curve. So we can use what we know about the geometric shapes to evaluate integrals as well. So if we say y is equal to the square root of 9 minus x squared, the hope is that we can recognize that that's really a semicircle that has radius 3. So if we were to say, what's the integral from -3 to 3 of the square root of 9 minus x squared, even though we may not know at this point in time how to do that integral, how to do the calculus part, we know that the area of a circle is pi r squared, so the area of a semicircle would be pi r squared divided by 2. We can see that this has radius 3, and so this is going to be 3 squared is 9 pi over 2, and use that as an argument to say that must be what that integral is equal to. We can also, if we understand the idea of what this integral is, if say this is a and that's b, and we get a curve that does something like that, maybe suggestive of a sine curve or something like that, then we know that if we look at the integral from a to b, if we knew, say, that these areas were the same, and if we knew that was, say, 5, then the integral from a to b, I'm going to call that f of x dx, we know that this area would be 5, but because it's below the x-axis, and remembering that this integral comes from that infinite sum of f of c sub I times delta x, so I going from 1 to n and the limit as n goes to infinity, but because it comes from evaluating that function, and that function, since it's below the x-axis, will be negative, that what we're going to get here is going to be the negative of that area we got here. That would make that integral be a -5. Now, by the same token, if what we wanted to know was really the area, and we wanted to know the true area between, say, f and the x-axis from x equals 0 to x equals b, then we could do this one of two ways. We could say that true area, and we could say the integral from 0 to a of f of x, because that part's above the x-axis, we know that's going to be positive, and area must be positive, and then we could subtract the integral from b to c of f of x dx, because that minus would change that negative value here into a positive, which would then make it the actual area. Or we know we could say that area is going to be the integral from 0 to c, and then put that function f of x into absolute values. All right. Just one more thing to remind you. It's been a little while. So we need to have that calculator skill of using our numerical derivative. So if we had, say, the integral from 0 to 5 of e to the negative x squared, and we wanted to get an approximation to that, this is one of those integrals that does not have a closed form solution. That is, there is no way to do this pencil and paper. So instead, you're going to have to use your calculator, and remember, you're going to find that if you hit the math button, and then option number 9 is going to be that FN integrate, and then you can follow the suggestions there to plug in the limits, and you're going to have to put in the dx into that expression. And if you do that right, I believe you're going to get 0.886. So make sure we know how to do that. That's a must-have calculator skill. All right, very good.